All right, now in the last chapter we talked about standing waves and strings, but we were looking mainly at just the wave on the string. In this chapter we're looking at how that vibrating string can then produce a sound. So we're going to look at strings as sources of sound, and then we're also going to look at tubes as sources of sound. So as we talked about in the last chapter, any object can vibrate to produce a sound, be it a string, be it a drum head, be it a desktop if you strike it. Stringed instruments make use of strings, a stretched string, to produce a sound. So, as we looked at in the last chapter, if you have a string and you know the tension of the string, you know the mass per unit length of the string, and you know the length of the string, then you can calculate the frequency at which that string will vibrate. That in turn produces a sound wave that has the same frequency. So, in this chapter, we're going to be mainly focusing on the sound wave that results from that. But we've got to go back and look at the wave on the string that is producing that sound wave. So the pitch produced by a vibrating string will be equal to the frequency, the frequency of the sound produced by the vibrating string will be equal to the frequency of the vibrating string. Now the wavelength and the velocity of the sound wave will be different than the wavelength and the velocity of the wave on the string, because the mediums are different. But the frequency in both mediums will be the same. We've got the sound wave in air, and we've got the string wave on the string. So different mediums, but the frequencies will be common between the two. So we can adjust the tension, or adjust the mass, or just the length of the strings, and that produces a different frequency on the string, and therefore that produces a different frequency of the sound wave. Okay. Now, a string by itself doesn't move very much air, so the purpose of the box that an acoustic guitar is built out of, it's called a sounding board, or the half-open top of a grand piano, is to just give more area for vibration to occur, to move more air, and therefore create a more intense sound. So the purpose of this sounding board is just to give more space for vibration to occur. All right. So let's look at an example. This will mainly draw on stuff we looked at in the last chapter. Under what tension must a piano string that's 1 meter long with a mass of 0.0025 kilograms be so that it produces a fundamental tone of 645 hertz? And then what is the wavelength of the sound wave that this string produces in air? And we're going to assume that the air is at room temperature. All right. So remember that the fundamental on a string looks like this: one antinode and one node at the center. So we're looking at 1/2 of a wave here. The length of the string is equal to 1/2 the wavelength of the wave. That means that the wavelength of the wave is 2 times the length of the string, which we're told in this problem the length of the string is 1 meter. So the wavelength of the wave on the string is 2 meters. Right? So that gives us the wavelength. We know the frequency that we want is 645 hertz. Now we're asked, what tension must the piano string be pulled to? Well, we can get the tension from this equation. That the velocity of the wave on the string is equal to the tension, the square root of the tension over the mass per unit length. We've got the mass of the string, we've got the length of the string. Tension is what we want to find. If we knew the velocity of the waves on the string, we could figure this out. Well, by looking at the wave on the string, the length of it, we have the wavelength. We've got the frequency that was given to us in the problem. So we can first use this equation that is valid for any kind of wave to find the velocity of the wave. And then once we have the velocity, we'll have all the information we need to calculate the tension here. So I'm going to plug this information into this equation. The wavelength of the wave is 2 meters. The frequency of the wave, 645 hertz. So the velocity of the wave on the string is 1.29 times 10 to the third meters per second. Right. With this velocity, we now have all the information we need to use this equation to find the tension. So I'm going to solve this equation for the tension. First, I'm going to take the square both sides. That'll get rid of the square root here. So I have v squared is equal to ft over m over L. To get rid of m over L, I'm going to treat this as one quantity here. So I'm going to multiply this side by m over L and multiply this side by m over L. All right. So that cancels this out over here. That leaves me with the tension is equal to v squared times m over L. So the velocity, found that here, is 1.29 times 10 to the third. That number gets squared times the mass, which is given to us as 0.0025 over the length of the string, which is 1 meter. So we work that out, and we get a tension of 4.16 times 10 to the third newtons. Right. We then ask, what is the wavelength that this sound, of the sound wave that the string produces in air? So the frequency is going to be the same, okay? But the wavelength and the velocity will not be the same. I mentioned that we're going to assume that the velocity of this, that this wave is moving through air that's at room temperature. As we saw previously in this chapter, the velocity of sound at room temperature is 343 meters per second. The frequency of this sound wave is 645 hertz. We can use this to find the wavelength. This equation, remember, is valid for any kind of wave. We use this equation here when we're looking at the wave on the string. We can use it here when we're looking at the wave in air. This equation can only be used when we're dealing with the string. Okay? This one we can use for any kind of wave. So I'm going to solve this for the wavelength. So that is 343 meters per second over 645 hertz. So the wavelength of the sound in air comes to 0.532 meters. All right. So strings can be used as sources of sound.